All right, so we're starting here by practicing factoring. Yesterday we dealt with some in-depth factoring, gave you a new method for being able to factor some of these. And so this warm-up is really getting at the idea of all of these different types of factoring that we can do. That first one, first of all, I want to talk about how do I know what to use for it, so I'm going to start each one with that. You notice that in this problem, I have x to the 6th and I have x to the 4th up here. It's not x squared and x like I've been seeing on most of my quadratics. That tells me right now that since I got something that looks a little bit weird there, I'm actually not going to use the same kind of method that I would use actually on these three. In fact, the only kind of factoring we can do on this first one is to factor out a common monomial. That is, what's the one thing I can divide out of every single term? And you notice I can divide them all by 5. And so I'm going to pull a 5 outside. Now factoring basically means introducing the parentheses. So I do 5 and then parentheses. 15 divided by 5 is 3, so that's 3x to the 6th. Minus stays a minus. 35 divided by 5 is 7, so that's 7x to the 4th. And then the plus stays a plus. 55 divided by 5 is 11. And then we double check to make sure that we factored out the biggest thing. 3, 7, and 11. Nothing I can divide all of those by. And I do have x's in 2 of the terms, but not the last term, so I cannot pull any x's out. So yes, that is then as good as we can make it. That is completely factored there. All right, now the second one, x squared minus x minus 56. I see the x squared, x, and number. That tells me I'm doing the whole factoring quadratic strategy, where I know I'm going to end up in the end with 2 different sets of parentheses, looking like this sort of a thing. Since it's just a plain old x squared at the start, there's no number in front of it, it makes my life a little bit easier. Because in order to do this then, I just have to figure out what 2 numbers add to -1, that's the number in front of x, and multiply to -56. And so we think through all the different ways we can multiply to -56, and you should come up with a -8 and a +7. And so there's your factored form for that. The second one, or I'm sorry, third one now. For the third problem, again we have the x squared, x, and number kind of a setup. Now, when I see that, that again tells me that I'm going to end up hopefully with those 2 sets of parentheses. But I don't have a plain old x squared. I have a 4x squared. When you see the number in front of x squared, always start with the strategy that we used up here on this first one. Can you factor anything out of every term? Because if you can, it's actually going to make your life a lot easier, and it's going to get you the completely factored form when you're done. In this case, can we factor anything out of every term? Yeah, we can factor the 4 out of every term, right? And so when we do that, that's going to give me 4 times x squared minus 11x plus 10. And so when I then go and get my answer, that 4 is going to hang out front, and then I'm going to have my 2 different sets of parentheses from there, each with just a plain old x inside. And again, I know each one is just an x, not like a 2x or a 3x or something like that, because after I factored out that 4, I'm starting with just a plain old x squared there. So I'm seeing what adds to -11 and multiplies to 10. Sometimes we get a little bit of a blind spot with this combination. It's -1 and -10. Sometimes we get a blind spot when we have that 1 multiplied by something, just because so often we say, well, what can I divide it by except for 1? We're used to often ignoring the 1 possibility, but we do need to include it here. All right, and then for that last one, for this last problem, we see the 5 in front of x squared, and so I automatically think, okay, can I factor anything out of every term? But in this case, we can't. And yet I still have a quadratic. That tells me that I now need to employ the guess and check method that we learned yesterday, which means I can first construct it in the box, and I know the 5x squared goes in the top left, and the last term goes in the last box, so that's minus 21 down there. Now in terms of filling this in, I know in order to get the x squared, there's going to be an x and an x. And in order to make it a 5x squared, one of those has to be a 5x, and the other one just has to be x. because that's the only way to get 5, is 5 times 1. If you choose to write it as a 1x, just to make sure that you've remember that you've actually accounted for that, feel free, just in your final answer, make it a little simpler. All right, now it's a matter of how do I get the negative 21, and it's doing a little bit of guess and check along the way to see how can I do it so that those two numbers, those two diagonal numbers, are going to add to the positive 8. All right, and so we try some different things. How can I get the 21? Well, 7 times 3 jumps out to me first. And I'm thinking, in order to get the 8 in the middle, I'm thinking I'm going to want to try putting the 3 down this side and try putting the 7 over here. And let's see what that gives me. So if I multiply those through, I get a 7x here, and then I get a 15x here. Notice it is, in fact, a negative 21 here, so one of those has to be negative. If I make one of those negative, can I get a positive 8? Yeah. And so then it's if I make the 7 negative. So then I carry that negative up, and that's what the box would look like. And so my final factored form, then I read it across the outside. From the top, it's 5x minus 7. And then down the left side, it's x plus 3. That is our correct factored form. And yes, if you wrote it as x plus 3 times 5x minus 7, yes, that's also correct. It's just the stuff inside the parentheses has to be the same. But the order of the parentheses themselves doesn't matter. So we're going back to graphing from standard form because this sometimes gets a little bit rusty. And so a quick refresher on this first one, then I'm going to let you loose to do them more and more on your own. Remember that when we're graphing from standard form like this, the very first thing we need to do is find out where the vertex is. Now, do you remember the equation we use for vertex? It is x equals a negative b over 2a, which in this case is going to mean that it's going to be a negative. B here is negative 30, so I'm going to do negative 30 there, over 2 times a. A here is a negative 5. Now there's lots of negatives flowing around in there. I wait to simplify them until the very end. All right, so we go ahead and we simplify that. On the bottom, that 2 times negative 5 is negative 10. And negative 30 divided by negative 10 is a positive 3. And then this negative that was out front, it carries down. So that means it's now a negative 3. All right, that can't be simplified anymore. That is our x-coordinate of our vertex. So I know my x-coordinate is negative 3. Now to find the y-coordinate, remember that we plugged that back into the original equation. So I now go y equals negative 5 times a negative 3 squared minus 30 times a negative 3 minus 40. Then go ahead and figure out what that gives you. And when you do that calculation, you should find that the y-coordinate is 5, which means that the vertex of this equation here is going to be at negative 3, 5. And now that we found the vertex, we can go ahead and make our graph. Because we start making our graph by plotting a point at the vertex, so I go negative 3, 5, plot a point there. And then, is this graph going to go open up or down? Down, because this is a negative in front of the x squared. And then, normally, if it were just negative x squared, I'd go over 1, down 1. But that 5 out front, that's a vertical stretch by a factor of 5. So that means I'm going down 5 times this 4. So instead of over 1, down 1, it's over 1, down 5. And then instead of over 2, down 4, we'd go over 2, down 20. Because I'm multiplying whatever I normally go by the 5 here. And 4 times 5 would give me 20. The 20 is off the graphing grid. And so I'm going to go ahead and just plot those 3 points and draw my curve in that goes through those. Now, having done that, hopefully everything has kind of come back to you on how you approach these. So go ahead and please graph this equation now. All right, so we go through all the work. We find our vertex is going to be at 5, -6. Plot that point. And then we can draw the rest of the graph in from there. Instead of over 1, up 1, this one's going to be over 1, up 2, because whatever we would normally go up by, I'm multiplying it by that 2. Whatever's in front of x squared, that's our stretch. So I go over 1, up 2 on both sides. And notice I'm going up because it's positive 2. And then instead of over 2, up 4, which is what I normally would do, I'm going to go over 2 and up 8. Again, when I count that out, I'm counting from the vertex. Instead of over 3, up 9, I'm going to go over 3 and up 18, which is just off my graphing board. So that tells me to go ahead and then draw the curve in that goes through those points, because I've plotted all of them that fit on my grid. And then as you go to graph this one, let's not let the fraction throw us off in doing the calculation. Show your work, you should be okay with it. Now oftentimes when we first do this one, plugging the 1/2 in there can be a little bit intimidating. But you'll notice that what happens when we plug in the 1/2 is that down here on the bottom when I do the 2a, 2 times 1/2 just ends up equaling 1. So it actually ends up working out fairly nicely. So your x-coordinate that you should have found is -2. Then plug that back in and proceed from there like normal. Okay, then when you plug that back in, you should be finding you have a y-coordinate of -9. And so your first point is going to go at -2, -9. So we plot our first point here at -2, -9, where we found our vertex was. And then each time we go up, we're going up half as far as normal. So instead of over 1, up 1, it's over 1, up 1/2. And then instead of over 2, up 4, it's over 2, up 2. Because half of 4 is 2. And then instead of over 3, up 9, it's over 3 and up 4.5. Because half of 9 is 4.5. And so notice it's every single time it's whatever I would normally go up, I'm just cutting that in half. So 4 and 16 becomes 4 and 8. And then from there, of course, we keep going. 525 becomes 512.5. And then 636 becomes 618. And then we're basically have filled up our grid as far as we can go, and you draw your curve in there. All right, and now we're going to shift gears a little bit here. There's one last topic we want to take a look at today. It's a bit of a departure from what we were just doing. And we're going to start by filling in this table because it's related to those graphs, but it's going to be a very useful table going forward. So please copy this down onto your paper and fill in, please, the missing values. All right, and when you filled in that entire table, this is what you should be getting. Now, this list of numbers down the right-hand side is going to be a very important set of numbers for a lot of different things that come up along the way in math, and especially today. This list of numbers is, in general, called the list of perfect squares. And you notice they're called perfect squares because all of them are what we get when we square a whole number. Those are numbers that you're going to be specifically looking for as we get into today's work. Because today we're going to be simplifying radicals. In order to do one as an example, please write down this problem. I'll walk you through it here together. So we have the problem here, 5 root 72. And we're being asked to write it in simplified radical form. When we see 5 root 72, remember this really means 5 times the square root of 72. So the 5 is just going to hang out front of the work we do until we're done. All right, so the way that I approach this is I'm going to be looking for the biggest perfect square that goes into 72. When I say goes into it, basically what I'm saying is, what can I divide 72 by? What perfect square can I divide 72 by? Now, there's actually a lot of them. I can divide 72 by. But what's the biggest one? And so as you're looking for it, you might start at 72 and kind of work your way up the list from there, from bigger to smaller. So like 64, yeah, 64 is less than 72, but it doesn't divide into it. So I can't do 72 divided by 64 and get a whole number, so that one doesn't work. I would try 49, it doesn't work. I try 36, and it does work, yes. And so then 36 then is the biggest perfect square that goes into 72. So now what I do for my work and how I use this is the 5 keeps hanging out front, and I then split the 72 into 2 separate square roots. The first one is that biggest perfect square that we just found, the 36. The second one is, well, 36 times what is 72? 2. So it's whatever that is. Notice that these 2 square roots, if I multiply them together, I get the 72. I get what I started with. All right, now the reason why we looked for the biggest perfect square is because I can now simplify that square root. What is the square root of 36? 6. And so this becomes 5 times 6 root 2. All I did was actually take the square root of 36 and turn it into 6. Now, I've basically simplified the root 72 now. I've turned the root 72 into 6 root 2. But I started with that 5 that was out front of it. So now I got to deal with that last little bit. I can do the 5 times the 6. That gives me 30. The root 2, well, it just stays a root 2 there. This is then considered simplified radical form. 30 root 2. That is 30 times the square root of 2. Whenever you're giving answers in exact form, and that ends up meaning there's a square root involved, you're going to need to be able to give it in this simplified radical form like this. Okay, I'm going to take a look at the first one, make sure you're heading in the right direction. So for the square root of 98, I start by looking to see what's the biggest perfect square that I can divide into 98. Now you might try 98 divided by 81, divided by 64, but you're not going to find anything until 49. So root 98 equals the square root of 49 times the square root of 2, and then I simplify the one that I can actually find, which is the square root of 49. That is 7. So my answer then is 7 times the square root of 2. Okay, then on to number 2. With number 2, that 4 out front stays out front. And then I start looking for the biggest perfect square again that goes into 432. And as I work my way down the list, I actually find a nice big one. 144 goes into 432 3 times. And so then the square root of 144 is 12. Root 3 is just root 3. We don't know what that is. And so we do the 4 times the 12, which gives me 48 root 3. There's your final answer for number 2. All right, number 3 now. You start looking for the biggest perfect squares, and as I start looking through it, I end up having all sorts of trouble finding many of them. In fact, the only one I ended up finding was 4 that went into 840. So I start by writing it as root 4 times the square root of 210, because 4 times 210 gives me 840. Square root of 4 is 2, so I have 2 times the square root of 210. Now, if you find yourself in this situation where you still got a really big number in there, you might be wondering, did I really find the biggest perfect square? And so you can take a look at the 210 now and see, are there any perfect squares that go into that one? And in this case, the answer is no, which tells me that actually this is as good as this one's going to get. So the final answer is 2 times the square root of 210. And then for our last one, square root of 41, well, you notice that square root of 41 is a prime number, which if you knew that already would make this a lot easier, because if it's a prime number, there are no perfect squares other than 1 that go into it. And I'm not going to worry about factoring out 1 over and over again, because we could always factor out 1. And so since there are no perfect squares greater than 1 that go into it, the simplified radical form is just what we started with. It's just the square root of 41, because it doesn't get any better than that.